All right, in this week's lab, we're going to be working with igneous rocks. Igneous rocks are those rocks that form from magma, cooling and crystallization of that magma. Discrete minerals are formed. Those minerals brought together in different proportions to form our different igneous rocks. Now, in working with the igneous rocks, we're going to make observations of their texture and their composition. Texture is referring to the size of the mineral crystals and also the proportion of empty or void space called vesicles, which are left by gases escaping from the magma as the rock crystallizes. In looking at the texture, we're getting insight into the conditions under which that igneous rock formed. Did it cool slowly underground, producing large mineral crystals, an intrusive igneous rock? Did it cool rapidly at the surface, producing small or fine mineral crystals and extrusive or effusive igneous rock? Or did it have sufficient gas when that magma reached the surface to erupt explosively, producing pyroclastic rocks like pumice, ash, or scoria? The other observation we make is composition. Composition is talking about the proportion of light and dark colored minerals. The color of the minerals is reflecting the composition or elements needed to make those minerals. Dark colored igneous minerals such as olivine or pyroxene, they're dark in color because they're iron and magnesium rich minerals. You know those minerals are called mafic, and they are found in greater proportions in igneous rocks that are mafic in composition, such as basalt. Minerals that are lighter in color, this could be white, clear, or even pink. These are minerals that have higher amounts of light color elements like sodium, potassium, or silicon. These are our minerals that make up much of the felsic igneous rocks, such as granite and rhyolite. So let's start with composition first. Composition, we're going to be looking at the proportion of light and dark colored minerals in the rock. Dark colored minerals indicate those minerals that are iron and magnesium rich. What I'm going to do is I'm just going to group my minerals, or group my rocks, into mafic, intermediate, and felsic. Mafic, mostly black or green colored rocks. These are rocks that are made mostly of iron and magnesium bearing minerals. Those would be minerals such as olivine, which is a green color, pyroxene, which is a very dark green color, or amphibole, which is a black color. Now, sometimes iron can have a different oxidation state, which gives it a more reddish appearance. But nonetheless, this is still a mafic rock made mostly of iron magnesium bearing minerals. Our felsic rocks are those rocks that are made mostly of light colored minerals. Now, felsic includes pink colored minerals. That pink color comes from large amounts of potassium bearing feldspar. So felsic igneous rocks rich in sodium, potassium, and silicon often have a high proportion of pink colored minerals. All of these rocks here, mostly light colored minerals, including pink colored minerals. Then our intermediate rocks are those rocks that have a more equal mixture of light and dark colored minerals. Easiest to see in this sample here, which has the larger mineral crystals. We can see a more even mix of white and black colored minerals. This rock is intermediate in composition, formed from a magma such as andesite. So what we've got now is we've got our mafic rocks, dark colored, rich in iron, magnesium bearing minerals, our intermediate rocks, which have a more equal mix of light and dark colored minerals. And over here, we have our felsic rocks containing mostly light colored minerals, including pink colored minerals, which represent the potassium bearing feldspar. The next thing we want to do is consider the texture of these rocks. Coarse grained textures seen in intrusive rocks, fine grained textures seen in effusive rocks that cool quickly at the surface, and pyroclastic textures, those rocks that are both very fine grained and also have a lot of empty space or void space called vesicles left from the escaping gases. What I'm going to do is I'm going to arrange my rocks into 3 rows: pyroclastic, effusive, and intrusive. Those pyroclastic rocks are easy to recognize because they are noticeably light or low in density, because the rock is made mostly of empty vesicles left from the escaping gas. This rock is a lot lighter than you would expect for a rock of its size. It's a pyroclastic texture. Here we have another pyroclastic texture. This rock still has plenty of empty spaces, vesicles, but the rock is still fairly high in density. This is a vesicular texture. Vesicular textures form when you have a low viscosity magma like basalt reaching the surface. While it still has a lot of gas, but the low viscosity allows those gases to just easily escape out of the magma rather than requiring an explosive or pyroclastic eruption to degas that magma. So here we have a vesicular texture. This guy is a lava bomb, another light in density rock, pyroclastic texture. This rock, it may be hard to see on camera, but the mineral crystals are pretty large. By large, we're talking about crystals that are easy to see without the use of a magnifying lens. This is an intrusive texture, a rock formed when magma crystallizes within the crust at slow rates, allowing large mineral crystals to form. This rock has much smaller mineral crystals. There's no vesicles or empty space in the rock, or very few to speak of. But the mineral crystals are very hard to see without the help of a magnifying lens. It's a fine-grained, effusive texture. So all these rocks are mafic in composition. They have a similar elemental composition. They have similar types of minerals, iron, magnesium-bearing minerals, but they have different textures reflecting the way that that magma was cooled. Our pyroclastic textures, the magma had sufficient gas to drive an explosive eruption, and we produce rocks like cinder, scoria, or lava bombs. A vesicular texture, gas present in the magma when it reached the surface, but the low viscosity, thin fluid nature of that magma allowed the gases to easily escape out of the cooling rock without requiring an explosive eruption. So this would be a lava flow, and gases are just bubbling out of that lava flow as the rock crystallizes. Then we have a dense, low gas, but still fine-grained rock, mafic in composition, reflecting rapid cooling at the surface, but the magma had already lost most of its gases. And then we have a rock with larger mineral crystals cooling at a slower rate intrusively within the crust. I'm going to do the same thing for my intermediate and felsic rocks. Identify the one with a pyroclastic texture. It's a rock that has very low density, reflecting the presence of lots of empty space in that rock from escaping gas during an explosive or pyroclastic eruption. Put our pyroclastic rock up here at the top. This is obviously our intrusive rock. We have relatively large, easy to see mineral crystals reflecting a slow cooling rate within the crust. These rocks are both high density. There's very little empty space or vesicles left from escaping gas. This material had already degassed before it started to solidify. We see a difference in texture. This is the finer texture. Mineral crystals, generally very small. There are a few larger crystals within the rock, light-colored crystals. Those are crystals of feldspar, plagioclase feldspar. Crystals that formed at a slower cooling rate, allowing those crystals to become slightly larger. Most of the rock is a very fine-grained material with the mineral crystals, individual crystals, difficult to see. This mix of two distinct crystal sizes, we call that a porphyritic texture, reflecting two distinct cooling rates. The larger crystals form solely underground. The magma was then erupted at the surface, including the already formed crystals within it. The remaining magma cooled rapidly at the surface, producing the fine-grained matrix that we see in this rock. Then we have this guy here. Mineral crystals are noticeably larger than they are in this rock, the effusive rock, but a little bit smaller than this rock, the intrusive rock. Something in between. I would still describe this as an intrusive texture because the mineral crystals are much easier to see than they are in this rock. And we'll do the same thing with our felsic rocks over here. Let me get this out of the way so it's not blocking your view. Again, we have this rock is low in density, lots of empty space left from the escaping gas. It's a pyroclastic rock. Here's our fine-grained rock. Most mineral crystals are very small. Again, a few embedded larger crystals, but by and large, the bulk of the rock is made up of very fine crystal sizes. This is our effusive rock. These rocks both have large, easy-to-see mineral crystals. These are both examples of intrusive textures, slow cooling rates, resulting in large crystals. Finally, we're left with this rock. Most of you recognize it as volcanic glass or obsidian. Obsidian forms when the magma is able to cool without individual mineral crystals forming. Basically, the magma freezes rather than crystallizes. Those conditions to form obsidian are relatively rare. But nonetheless, obsidian is an easy to recognize rock because igneous rocks are mostly silicon, same thing that glass is made out of. Obsidian has a texture very similar to glass. This particular rock is about 70% silica, so it has the physical properties that we associate with glass. Very sharp edges and conchoidal surfaces formed by fracture, leaving concave indentations. You see a similar surface when you look at the edges of broken glass. So this is a material that formed cooled very rapidly, but under conditions that didn't allow distinct mineral crystals to form. So it's an example of an effusive texture, a special type of effusive texture called vitreous or glass-like. Now, this particular obsidian is easy to recognize as felsic. This variety of obsidian is called mahogany. It's a mostly red in coloration, reflecting lots of potassium in this rock, an indicator of a felsic composition, what we would get from a rhyolite magma. Most obsidian that you'll see is jet black in color. Nonetheless, it's still rhyolite in composition. You might be fooled into thinking your jet black obsidian is mafic, but the conditions to form obsidian, although rare, occur most commonly in rhyolite magmas that have lots of water in them. Why does the obsidian appear black even though it's felsic in composition? It's because the individual minerals did not crystallize and segregate out those mafic elements, iron and magnesium. This rock is felsic, but it still contains about 10% iron and magnesium. Making chocolate milk is a good analogy to making obsidian. You have your glass of milk. Milk is white. Think of milk as felsic in composition. You add some chocolate syrup to your glass of milk. Say 10% chocolate syrup, 10% mafic material. If you were to mix that glass up, distribute our chocolate evenly through the glass, the entire glass of milk appears dark in color, even though it's still 90% milk, 90% felsic, and only 10% chocolate, 10% mafic material. Obsidian is the same way. Our 10% or so of mafic materials didn't segregate out into discrete minerals as they did in this intrusive rock. Instead, those mafic materials are mixed throughout the whole rock, giving the rock an overall dark appearance, even though it's only 10 or so % mafic material.